and leave the floor to our second keynote speaker, our very own Anders Lyngfelt, Professor Anders Lyngfelt. He's been a professor for many years here at Chalmers University of Technology at the Division of Energy Technology. His early works were about abatement of SO2 emissions from fluidized bed boilers. And the last 2 decades, he has focused on chemical loop and combustion and CO2 capture. He is, of course, the initiator of this conference. And he's written more climate songs than anyone I know. So please welcome Professor Anders Lyngfelt.
Yeah. Thank you. I can start to say that one of my climate songs is actually dedicated to the previous speaker, James Hansen. Okay, I'm very happy to see all of you here, and it's a dream come true for me to see all of you engaging in negative emissions coming together with leading researchers of the world in this area. And most of all, I want to thank Carl Linderholm for engaging in this, organizing this conference. It's actually a mistake, me standing here. I always had the very strong opinion that I shouldn't be doing these kinds of things because my biggest impact on climate would be to do what I'm best at doing. That's actually chemical looping research. But the reason I'm standing here is that 2 years ago it was a bit gloomy. I didn't have the funding coming in for the expensive experimental research we were doing, and I was facing a loss of key competence like Carl. So I was advised I should perhaps start thinking about doing something else, and I thought, okay, let's be a climate activist. So I wrote an article, debate article for the biggest newspaper in Sweden, and the day I was going to send it in, together with some of the people in the committee and other researchers here at Chalmers. But the day I was going to send it in, I was eating breakfast and opening this paper, and there was a terrible debate article about how bad negative emissions were. So I wasn't too happy at the time, and I wrote there were actually 3 very angry replies on this debate articles, one from me, and the others from people who are also at the conference. And I had been working on trying to get a lunch seminar. The energy area of advance in Chalmers has lunch seminars. And I wanted to present my research on negative emissions there. But it didn't come out so well, because there was eventually a lunch seminar. But the title of the lunch seminar was something like Negative Emissions, a Dangerous Game or Necessary for the Climate. And I wasn't really happy about that. I thought, why should I have to present my research in such a context? And the people who wrote the debate article in Dagens Nyheter were invited for this. But what actually happened at this conference was that we agreed entirely. negative emissions are a dangerous, truly a dangerous game, in the sense of seeing it as a primary solution to the climate problem, in the sense of expecting very large emissions of CO2 in a distant future to solve the problem, of leaving our grandchildren with a burden and responsibility to clean up our emissions, and as an excuse for not doing rapid reductions of fossil emissions. But it's still necessary. So this is a question of balance, dangerous game, and necessary to save the climate. So the Paris Agreement says we should stay well below 2 degrees and pursue to limit to 1.5 degrees. And this gives us a carbon budget, which is, for the latest numbers, I think 3 to 19 years of today's emissions. And that's not realistic, so we need negative emissions. So the 2-degree the 2-degree target budget will be spent in 2042 or something like that, with even if we manage to decrease our emissions rapidly. So we need a lot of negative emissions in the future. And, well, this is a more complex diagram showing the same thing, which is also the a sort of a median of all the 2-degree scenarios of the IPCC. And this includes a very large negative emission. So compared to the 800 gigaton of budget still there, it's almost 600 or 700 gigaton CO2. Which corresponds to around 100 tons per now living human being. And if it costs 100 euros to capture CO2, that's a cost of 10,000 euro per now living human being. And that's the burden we leave to our grandchildren. So, and I think that's totally irresponsible to base climate policy on leaving this burden of removing our emissions to our grandchildren. And it's equally totally responsible not to start using negative emissions, as well as all other available means of reducing fossil emissions. And I think starting to do negative emissions will also help us understand the absurdity of releasing CO2 for free. And I agree with James Hansen, we need a cost. We need the invisible hand of the market to find all the solutions we need. There are a lot of solutions which are known and unknown and which are not being done just because we emit CO2 for free. And we have failed for 25 years now, since 1992, to put a price on CO2 emissions. And we need to make the market work for the climate, not against the climate. So this is not the invisible hand, that's the very visible foot that tramples down most of our efforts. And I hope the next Nobel Prize in Economy will award the discovery of the visible foot that trips up all our attempts to solve the climate issue. I mean, that's what I've been hearing during 20, 15 years of research from the industry. We want to do this, but it's got to be business. We see no business case. So, negative emissions, most negative emissions are based on the concept of preventing CO2 which is captured by biomass to return to the atmosphere. I think that's the important thing to have in mind. Biomass captures CO2, we don't want a circle here, a cycle. We want to break this cycle and stop the CO2 from going back. We take out a lot of biomass by forestry and agriculture. We turn it to food, fodder, fibers, and sometimes chemicals, or to energy. The fodder and food that's eaten comes out as CO2, but the rest comes out as a waste or as products. The products can be recycled, but eventually they can be turned into waste, including pulp liquor, which is a waste, which is produced, which we get when producing paper. And there's a lot of, if we burn all this, there's a lot of CO2 to be captured. So we can burn waste, we can burn biomass for energy to reduce fossil emissions, but we can also take the advantage of all of this combustion to capture the CO2 to provide negative emissions. We can also use biomass to produce biochar and put it in the ground, together with producing liquid and gaseous fuels, or just burning the gas from the pyrolysis needed for producing biochar. The only for the energy use, there's only really one conflict between BECCS, that is bioenergy capture and storage, negative emissions, and that's if we do liquid and gaseous fuels of the biomass, then we produce something that's used in vehicles and releases carbon dioxide to the air. But most processes for converting biomass to liquid and gaseous fuels actually produce a lot of CO2 because they have so there's a possibility to combine even the production of liquid and gaseous fuels with negative emissions. On top of this, we can use the forestry and agriculture to produce negative emissions by biospheric storage, storage in the biosphere. So I think we should look at biogenic CO2 as a valuable waste that can be used to amortize our gigantic climate debt. So how much is there? I don't know. Here are some numbers. We note first the fossil emissions are around 35 gigaton per year. Modern bioenergy is only 1 gigaton per year of CO2, whereas total bioenergy is around 5 gigaton per CO2. Here are some numbers for the potential. They vary greatly, and I think the discussion will continue how much there is. I note the green in the middle there, the total biomass harvested corresponds to 20 gigaton per year, which is actually more than half of the fossil energy. About a third of this, I have estimated, is what we're breathing and what our livestock is breathing. But the rest could perhaps be used as a waste for producing negative emissions. There are a number of estimates for how much residues we can use for CO2 capture or for energy production. So the expected needed nets vary a bit from 5 to 15 gigaton per year in the IPCC scenarios. But I note if we could do 5 gigaton per year, we could in 7 years compensate for 1 year of fossil emissions right now. But it's 5 gigaton is an enormous amount. It's not an easy thing. Another thing I want to point out is that biomass is a limited resource. It must be used efficiently with respect to climate. So, and if we look at different ways of using biomass, we can use it to produce power and heat. We can use it to produce power and heat combined with CO2 capture. We can use it to produce fuels, or we can use it to produce fuels in combination with recovering the waste CO2 stream. So I define the total climate efficiency to be the added efficiency of reducing the emissions of fossil CO2 and removing CO2 from the atmosphere. And a simple diagram shows that if we do both, the climate efficiency is twice as big when it comes to producing power and heat. If we produce fuels, the climate efficiency is less. But we should consider that the upper row here, the climate efficiency for reducing fossil emissions, that could be distinctly lower. I mean, sometimes or often we have other alternatives to reducing fossil emissions. So to be on the safe side, to really make a big impact, I think the safer side is second row, which is prioritizing using it for negative emissions. So, but that's more costly normally. So the discussion has been that the negative emissions are a non-existing technology. I would say that BECCS uses CO2 capture and storage technology, and so does it exist? Well, this plant was supposed to have started in 2014, unless it's fake news. But the one who started this is actually here today, Mike Monia, and we will hear him talk. And I hope he can persuade us that this is existing technology. This is capturing 1 million tons of CO2 per year from the flue gas of coal. And it shouldn't be more difficult to recover CO2 from the flue gas of biomass, unless, at least if the plant is sufficiently big. So, and here's another one, started in 2017. And here's an example of storage. There will be more talk on storage and capture later today, but I can't help showing this. This has been going on for more than 20 years, 1 million tons per year in the North Sea. It's stored in a huge aquifer. It has an enormous volume. The area is 26,000 square kilometers. The height is 200 to 300 meters. It has a high porosity. And if all this volume could be used, it cannot, of course. We can't use all of this volume, but several percent perhaps. But the total volume corresponds to Europe's CO2 emissions from fossil fuels today during 800 years or so. So it's a huge volume, and there are other places to store CO2 as well in Europe and the rest of the world. So total storage today is around 30 megaton of CO2 yearly, or 0.1% of global emissions. And only 1 megaton per year is BECCS of this. But the technology exists despite incentives being very, very rare and very poor. So 0.1% is, well, it can be compared to where we had solar 5 years ago, which was a bit less than 0.1% of the global energy production. It's up to 0.5% now, so it's rising quickly. Wind power was 0.4%. So the really big renewable is still bioenergy. So, I said there is a cost for CO2 capture, and that's a problem. That's something we can improve, I believe, because the big cost is gas separation. For every ton of fuel, we have like 10,000 cubic meters of gas that has to be cleaned, and molecules are very small. But there are existing technologies, as I've said. But there is a technology where we can do this without gas separation. It works just like the blood that transfers oxygen from the lungs to the muscles and the brain. So what we have is two reactors, an air reactor and a fuel reactor. And a metal oxide that transfers oxygen from the air to the fuel. So the combustion products, which are carbon dioxide and water, because of the fuel contains carbon and hydrogen. But the water is easily removed by condensation. So ideally we can get a perfectly clean stream of CO2 without doing any gas separation. No active gas separation. Because we never mixed the air and the fuel. We can do this process without mixing air and fuel. And for this reason we don't need any active gas separation. So, but this is of course the cliffhanger. This is an elegant process, but does it work in practice? So I've spent 20 years of showing that it can work. And the first 5 years it was only a paper, a desk concept. But yes, it works. And we have shown this in 4 different pilots with 4,000 hours of operation. We've shown it with gaseous fuels, we've shown it with liquid fuels, and we've shown it with solid fuels, the 2 pilots to the right. So, this, and yeah, worldwide there is even more operation, so 10,000 hours in 35 pilots. And this technology is very similar to a very common technology for burning biomass, which is called circulating fluidized bed boiler. It doesn't need to be circulating, it can be without circulation also, fluidized bed boiler. But it looks like this. And the similarity is very great it's very similar to chemically looping combustion. We have air going into the air reactor. Sorry, this was in Swedish. Luft is air. So the air and the bränsle is fuel. I apologize. So the air reactor is to the left and the fuel reactor is to the right. So we add air, which provides the oxygen and also causes the circulation, just like in the circulating fluidized bed boiler. But then we add a fuel reactor to the right, where the fuel is added. So it's because of the similarities, there is a low added cost for building a CLC compared to conventional combustion. So I'll just explain what the fluidized bed is. If you blow air through a bed of particles, for instance sand, which is normally used in fluidized bed combustion, you get what's called a fluidized bed. And the reason it's called fluidized, it's because it behaves like a liquid or a fluid. So this is what the fluidized bed, circulating fluidized bed looks like. The particles eventually come to the cyclone and fall down. So this is a cold flow model. Now, a fluidized bed boiler. On top you can see fluidized bed boiler. It's top view, side view and front view. This has 6 cyclones. It's very big. It's not the biggest in the world, but it's one of the biggest in the world. 1,000 megawatt thermal. And below you can see the difference. That's a 1,000 megawatt CLC boiler, chemical looping combustion boiler. And the big difference here is the fuel reactor in the middle. So for many years, I guess more than 10 years, I was very worried about the cost, the gigantic cost for this fuel reactor, which is an added cost. So eventually I started to calculate the cost difference. And we have a conservative estimate is that it's more than 2,500 square meters at a cost of around 1,500 euro per square meter. So we're talking about 4 million euro of investment, which with a depreciation of 10% per year would be a cost of 0.4 million euro per year, which is to be divided by the 2 million tons of CO2 which would be captured by a power plant this size, which gives a cost of 0.2 euro per ton of CO2. And that's less than 1% of the estimated cost for CO2 capture and storage. So I guess you won't believe me. And you shouldn't, because there are other costs coming in here, like the compression of the CO2. But somewhere here we have the fundamental cost. And I did this same calculation for a much smaller biomass-fired CLC boiler. And because it's much smaller, the cost comes to twice as much, 0.4 euro per ton of CO2. And I could say, so I round up this estimate to 1 euro per ton to be a bit conservative in this calculation. So here are the added cost. CO2 compression is we believe is the biggest cost. There's also what we call Oxy Polishing. We don't expect to get 100% conversion of the gas in the fuel reactor when we do solid fuels. We can reach 100% with gaseous fuels, no problem, but a bit more difficult with solid fuels. So we have between 75 and 95% conversion of the gas. So we need to add some extra oxygen. But it actually means that we can reduce the need for gas separation with a factor of around 10, which gives a big reduction in cost. So the estimated cost is around 20 euro per ton of CO2 if we add all this oxygen carrier and steam for fluidization. So, I believe we could do a demonstration of this technology as a much lower cost, because to demonstrate the technology, we don't do the Oxy Polishing and the CO2 compression, which are the big costs. I'll come back to them. We have different negative emission technologies which have different safety of storage and estimated retention time. What does this mean? Now I'm going to put a very difficult question. For how long do we need to store the carbon? Do we need to store it for eternity? So here are some examples from these were the best numbers I could find. This is from a study in 2003. It compares a business as usual case, which is an enormous release of CO2, 20,000 gigatons, and to the right it's 8,000 gigatons. And it's compared to the case where we have no leak, where we store it with no leak. 80% of this large release is permanently stored, which is the lower curve in both diagrams. So I think these the upper curves correspond to 6 degrees warming and 3.5 degrees warming or something like that. So, but the other curves are more interesting because they show what happens when we store CO2 and if it leaks. So, and the assumption for the storage is that the fraction permanently stored increases with the time constant. So it's 0 in the beginning, and eventually it's bigger and bigger. So, and this time constant is for the left diagram, it's 7,000 years. So this constant is very long, so it doesn't affect the first curves really much. So the first curves are for more rapid release, 450, 900 years and 1800 years of retention time. And we can see that just shifting, making the release take place during a longer time period lowers the peak. So just by emitting the same amount more slowly, we can lower the peak, but we eventually reach the curve of the business as usual case, but we can get a lower peak. And as we increase the retention time, the peaks will be lower. And eventually to the right here we also see the effect of some of the CO2 being permanently stored. So what we can see here with this extreme release, we're not back to the starting point even in 15,000 years. So the natural processes which remove CO2 from the atmosphere are slow. In the case of the somewhat smaller but still very high release, we're actually back at the starting point, 410 ppm, after 8,000 years, which is a bit quicker. So, and we can see if the storage has a long retention time combined with part of it being permanently stored, we can see that we are well below the starting point. And this is now for a very, very big storage of CO2. Very, very big, 8,000 gigaton. I also point out that it's a very long period to go from 410 to 350 ppm in this no leak case. It's a millennia. So I think we need some help by negative emissions to get to where we want, even if we can stop it at 410 ppm, which is where we are today. So, but the median case for the which I presented previously was less than 800 gigaton, which is less than 10% of what we have in the right diagram. So I conclude that leakage should not be a problem if it's not too fast. I think that can be safely concluded, although we should do some more modeling on this to see what is an appropriate. But I think a mixture of different negative emission technologies with different storage time would be adequate. So what is a reasonable cost? The carbon dioxide intensity is around 0.5 kilogram per CO2 per euro. If multiplied by a tax or a cost for avoiding emissions, you get the tax as a fraction of the global GDP. Thus, if the tax is 2 euro per kilogram, you get something which is 1 if you multiply these. So the tax would be 100% of the global economy, which is not possible today. But if we go down to 1% of this, 0.02 euro per kilogram of CO2, the fraction would be 1%, which is more reasonable. So we can estimate what's a reasonable cost approximately. So CLC is happens to be about 0.02, which I think is a reasonable cost. I think CCS estimated cost is also a reasonable cost, 2.5 degrees. So and that's also what's said to be the price needed now. The price will need to be at least 0.05 euro per kilogram or more if we're going to take this for real with climate change, and it will need to rise perhaps to 0.4 euro per kilogram. So where we need to go in price is something like this, at least according to Rockström et al. And the cost of CCS and CLC should be much lower than this. So, and there is possible storage in the Nordic countries, in the North Sea outside of Norway, as I mentioned. And we have big CO2 emissions in Sweden from biomass, from large point sources. Yeah? Är det slut? Yeah. Okay, sorry. So we could reduce our emissions by more than 150%. So we have exceeded our legitimate share of the carbon budget twice in Sweden. And the value of these should be 10 billion euro, which is 2% of the CO2 emissions. So key messages. Balance. CO2 CCS is existing technology. BECCS is normally the most efficient way of using biomass. We don't need to store CO2 forever. CCS has reasonable costs. Negative emissions is not instead of other use of biomass, normally. It's using a waste stream. It's immoral to leave this gigantic debt to our grandchildren. We should start negative emissions now in parallel with rapid fossil CO2 emissions. Sweden has a very good position for negative emissions. And tomorrow I will discuss possible financing. And I have a dream that of a worldwide cost of emitting CO2 and not leaving an immense debt of CO2 to our children's children, and seeing a day when the CO2 starts to fall and meeting the 1.5 degree target and be back to 350 ppm. And a bit less important, that Sweden will be the first nation to be CO2 negative, to reduce the emissions by at least 550% and become a good example to the world, and that CLC is part of the solution. Thank you.